Hi everyone, myself Arjun. Today I'll be talking about structure of matter and its relevance in dentistry. Introduction. The principal goal of dentistry is to maintain or improve the oral health of patient. A wide variety of dental materials are involved in the clinical applications and the material should be carefully selected. Through understanding and experimentation, it is possible to maximize any one property, but in no application it is possible to select a material for one property above the other. Now it is precisely in the balance of one factor against another that the materials are used successfully. Hence, it is essential to know the properties of the dental materials to be able to understand the properties and reaction of the materials and predict the outcome. Now, interatomic bonds, forces that hold atoms together, are of the cohesive type. These interatomic bonds may be classified as primary and secondary, and in primary, ionic bond, covalent bond, or metallic bond, and in secondary, hydrogen bonding, van der Waals forces. The weakest of them is the van der Waals forces. Now, ionic bonds, mutual attraction of positive and negative charges. Example, sodium of 1 valence and chlorine of 7 valence. These type of bonds exist in certain crystalline phases of some dental materials such as gypsum and zinc phosphate cements. The clinical significance, glass ionomers cements are adhesive to enamel and dentin via ionic bonding of the glass ionomer of the calcium and phosphate ions of the tooth. Now, covalent bonds. In many chemical compounds, two valence electrons are shared. It occurs mainly in dental resins. Hydrogen is an example of this type of bond. Metallic bonds. Example, gold easily donates electrons from their outer shell and forms cloud of free electrons, resulting in the formation of positive ions that can be neutralized by acquiring new valence electrons from adjacent atoms. Chief characteristics of a metal is its ability to conduct heat and electricity. The conduction is due to the mobility of free electrons present in metals. Now, interatomic secondary bonds. They do not share electrons. Hydrogen bonds. The hydrogen bond, a positive portion of one molecule is attached to the oxygen that is a negative portion of its neighboring molecule. This forms the hydrogen bridge. Intermolecular reactions, example, sorption of water by synthetic resins, dental resins. Now, van der Waals forces, example, in inert gases, electron field constantly fluctuates. Its charges become momentarily positive and negative. Fluctuating the dipole is thus created that will attract other similar dipoles. Now, crystalline structure. Atoms combine in a manner that ensure minimal internal energy. A space lattice or crystal, a regularly spaced configuration of atoms that is known as space lattice or crystal form. Now, cubic space lattice is atoms crystallized in cubic arrangement. Some pure ceramics such as alumina, zirconia, core ceramics are entirely crystalline. Now, types of crystalline structures: simple cubic, body-centered cubic, face-centered cubic. It's close packing. Now, non-crystalline materials. Those are waxes used by dentists or laboratory technicians. Glasses are super cooled liquid. Now, resin-based composite consists of resin matrix, filler particles, and organic coupling agent that bonds the filler particles to the resin matrix. Now, composites have a non-crystalline matrix. Now, important part, the adhesion and bonding. In complete denture retention, adhesion between the denture and saliva and soft tissues. It's important. Now, the adhesion, when unlike molecules are attracted, is known as adhesion. The attraction of the like molecules is known as cohesion. Material or film produced for adhesion is adhesive. It can be fluid or semi-viscous is the best. The material to which it is applied is known as adherent. Now, adhesion, for example, you can see a thin film of saliva between the denture bearing area and the denture base. So here the denture base is being attracted to the outer mucosa and saliva being acting as the adhesive. Now, cohesion, attraction of like molecules of saliva aiding in retention. It is the attraction of the like particles and present in saliva. Now, interfacial surface tension, this thin film of saliva resisting the displacement forces and a little liquid air interference, as explained. Now, mechanical bonding, strong attachment, example screws, bolts, undercuts. These are examples of mechanical bonding. Enamel acid etching with phosphoric acid for 10 to 20 seconds forms minute pores and resin flows into the pores. It is an example of mechanical bonding in dentistry. Increased or improved mechanical retention causes decreased marginal leakage, stains, secondary caries, and irritation of the pulp. So, as explained, bonding is very important in dentistry. Principles of adhesion, surface energy, wetting, contactile angle of the wetting. Now, surface energy. At surface of lattice, energy is greater and outermost atoms are not equally attracted. Increase in energy per unit area of surface is referred to as surface energy or tension. Greater surface energy is greater capacity of adhesion. Now, wetting. The liquid must flow easily over an entire surface and adhere to solid. The formation of a strong adhesive joint requires good wetting. Now, contact angle of the wetting. When there is spreading of the adherent, it's almost 0 degree, the wetting angle, and good wetting is when it's less than 90 degree, and incomplete, it is incomplete, it's set as incomplete wetting when it is at 90 degree, and no wetting, it means 180 degree, the contact angle. Now we'll talk about physical and mechanical properties of matter and its relevance in dentistry. My content is an introduction, and we'll be discussing about the physical properties such as viscosity, creep and flow, color and color perceptions, thermophysical properties, tarnish, corrosion, galvanic current, and the mechanical properties, stress, strain, elastic modulus, strength properties, toughness, brittleness, ductility, and malleability, now and hardness. I'll be taking it as 2 sections. Now, introduction. Physical properties are the measure of material. Now, physical properties of tooth. This set the standard for materials attached to a tooth. So, the most equivalent properties of a tooth to the material used to restore is better. If a restorative material can be made to hold properties similar to those of natural structure, it should perform as well as original teeth. Now, viscosity. Liquids, when placed in motion, resist imposed forces that cause them to move, the frictional forces within the liquid. This resistance to motion is called viscosity. So we know the thickness of the and flow of the material. The elastic means materials that have mechanical properties independent on loading rate. And viscoelastic materials are materials that have mechanical properties dependent on the loading rate. The unit of viscosity is poise, and dental materials have different viscosities when prepared in their intended clinical applications. So we use different materials according to the properties or the properties we require at the situation of the treatment, and it different in different times. A liquid occupies the space between two metal plates. The lower plate is fixed and the upper plate is moved to the right with a certain velocity. There is shearing force. The upper plate moving with velocity v. The force F requires the moment which is produced by the friction of the viscosity of the liquid. The stress develops within the structure when an external force is applied, which causes a strain to develop. So if the plate have an area A, the shear strength is equal to force by area. The shear stress rate or the rate of change of deformation is V by D, where the V is the velocity of the liquid and D is the distance between the two plates. That the movement happening on the upper plate or the lower plate. Now viscosity is equal to shear strength by shear strain. So Newtonian is an ideal fluid demonstrating a shear strength that is proportional to the strain rate, and thus the plot is a straight line. Pseudoplastic material is an increase in strain rate produces a less than proportionate increase in shear stress. Thus the viscosity decreases with the increasing strain rate. Now plastic material. These materials behave like a rigid body until some minimum value of shear stress is reached. So it changes the property at that point. And diamond material is when the flow index value is greater than the unity, and increase in strain rate produces a more proportionate increase in shear stress. Thus, the viscosity increases. Now, the common flow behaviors of these three materials, or we have seen Newtonian, the pseudoelastic, the dielectric material. Now, creep. Time-dependent plastic deformation due to prolonged exposure to high temperature or stress, continuous stress. It is distinguished from the flow by the extent of deformation and the rate at which it occurs. It's seen very much evidently seen in long long restoration of amalgam. In metal, creep usually occurs at very high temperature near melting point. The metal used for cast restoration or substrates for porcelain veneers are not susceptible to creep deformation due to high melting points. The most important exception in dental amalgam, which has components with melting points only slightly above the room temperature. That's why it's seen most in amalgam restorations. Now flow. Flow implies a greater deformation produced more rapidly with a smaller applied stress. Flow is applied to amorphous materials. Example, silly putty, that is, it fractures at a rapid stretching rate. However, if it is placed at a sphere on a table, it will be flattened out under its own weight over time. So, and the waxes. The flow is a measure of its potential to deform under a small static load. Example, by pressing a hand. Now, color and color perceptions. Light, part of electromagnetic spectrum. So, color is a sensation in views from light of varying wavelengths reaching the eye. The cone cells of retina are responsible for the spectral sorry for spectral sensitivity. So it's the visible light for us from 400 to 700. Now, color perceptions. The phenomenon of vision can be explained by considering the response of human eye to the light reflected from an object. Light from an object that is incident on the eye is focused in the retina and is converted into nerve impulses which are transmitted to brain. The three dimensions of color. The color perception is described by three objective variables: hue, chroma, and value. These three parameters constitute the three dimensions of color space. The hue is defined as the particular variety of color, shade, or tint, example red, green, yellow. The chroma is the intensity of the color, degree of saturation, and particular hue. And the value is defined as a relative darkness and lightness of the color or the brightness of an object. The value of 0 is black and the value 10 represents white. This is the Munsell color system, and in this color system, with this we can understand the where the proper representation of hue, value, and chroma. And value, you can see it's coming from 0 to 10, that is black to white, and the chroma shows the intensity of the color, and the hue is the different type of colors or the different variety of color or shade or tint. Now, C-Lab color system. The Commission International TCIE and International Color Research Group published at the C-Lab color system in 1976. Now, color terminologies. The opacity. Opacity means the measure of impenetrability of visible light. Translucency means diffuse transmission of the visible light. The transparency means capable of transmitting light. Metamerism means same color seen as different colors in under different light. And the fluorescence means ability to transmit light. Now, thermophysical properties. Thermophysical properties can be simply defined as a material properties that vary with different temperature without altering the material's chemical identity. These are thermal conductivity, thermal diffusivity, and coefficient of the thermal expansion. Now, thermal expansion, conduction. Thermal conductivity of a material compared to with that of resin composites induces greater pulp sensitivity. Now, thermal diffusivity, it is measure of the rate at which a body with non-uniform temperature reaches a state of thermal equilibrium. Thermal conductivity of zinc oxide usinol is slightly less than that of dentin. Its thermal diffusivity is twice that of dentin. The thickness of cement base is directly related to its benefit as an insulator. Coefficient of thermal expansion. The coefficient of thermal expansion describes how the size of an object with a change in temperature. It measures the fractional change in size per degree change in temperature at a constant pressure. Tarnish and corrosion. Tarnish means tarnish is a surface discoloration of the metal or even a slight loss of luster. This surface discoloration is due to either the formation of hard and soft deposits on the surface, usually formation of thin films or oxides, sulfides or chlorides. The tarnish is often the first step of corrosion. Now, corrosion is not only a surface discoloration, but it is disintegration of the metal by reaction with its environment. Now, classification of corrosion, which is important. There are different types: dry corrosion and wet corrosion. And dry corrosion, metals and non-metals. It's seen in non-metals and non-metals. Now, wet corrosion means dissimilar metals, heterogeneous surface of composition, stress corrosion, and concentration cell corrosion. Dry corrosion means in which there is a direct combination of metallic and non-metallic elements. Electrolytes are absent, and example of oxidation, halogenation reaction. Electrochemical corrosion or wet corrosion. Corrosion occurs in the presence of water or some other liquid electrolyte. In mouth or saliva acts as in the electrolyte, and the materials are amalgam, crown, or the exposed metal areas. Now, dissimilar materials. Galvanism is a result of difference in potential between dissimilar restoration in opposing or adjacent tooth, which produce a current through the electrolyte saliva. Stress corrosion means degradation by the combined effect of mechanical stress and corrosive environment, usually in the form of cracking. For example, repeated removal and insertion of partial denture will develop a severe stress pattern of certain alloy, especially at the grain boundaries, and combined with the oral environment, the appliance develops stress corrosion, resulting in the fatigue and failure. Heterogeneous surface composition means a second type of electrolytic corrosion is that due to the heterogeneous composition of the metal surface. Example, this type may be in intactic and peritactic alloys. A common situation for this type of corrosion could be amalgam restoration with polished and unpolished surfaces or areas. The concentration cell corrosion means when two or more areas of the same metal surface are in contact with electrolytic solution of different concentration. Example, a metallic restoration which partly covered by food debris is different from the saliva, and this contribute to the corrosion of the restoration. Now, galvanic currents. As long as metallic tender restorations are employed, there seems to be a little possibility that galvanic currents can be eliminated. Galvanic shock means a pain sensation caused by electric current generated by a contact between two dissimilar metal, forming a galvanic cell in oral environment. So there will be a positive and negative area and the electrolyte passing the current. That is saliva. It can be a real source of discomfort for an occasional patient. Such post-operative pain usually occurs immediately after the insertion of new restoration and generally is gradually subsides as disappears in few days. Thank you. The next section will be continued.